Today, we are diving into something seriously powerful, an industrial process called Plasma Arc Welding. It's a technology that takes a concept you might be familiar with and, well, cranks the power way, way up. All right, so really get our heads around this, let's start with a simple picture. Think of standard arc welding, maybe you know it as GTAW, as being like the mist setting on your garden hose. It's wide, it's pretty gentle. Now imagine twisting that nozzle to the jet setting. That's plasma arc welding, or PAW. It's a single, high-pressure, super-focused stream of power. And that difference, that incredible focus, is the key to everything we're about to explore. So here's our game plan for today. We're going to see how PAW creates such a powerful arc, uncover the one secret that makes it all possible, check out its two very different modes of operation, look at the incredible keyhole technique, and then see where all this power gets used in the real world.
Okay, first up, a more powerful arc. You see, plasma arc welding didn't just appear out of nowhere. It's really a brilliant evolution of an older, very common process called Gas Tungsten Arc Welding, or GTW. It just takes those basic principles and gives them a massive performance boost.
So what is it officially? Well, PAW is an arc welding process that uses a constricted arc. That word right there, constricted, is the most important word in this whole explainer. By literally squeezing the arc, it creates this incredibly stable, high-energy jet of plasma that lets us join metals with amazing precision and speed.
So, let's talk about that secret. How does it get all that power? Well, it all comes down to one surprisingly simple but totally game-changing idea: arc constriction.
Yep, that's it. The secret is a squeeze. You see, a normal welding arc kind of spreads out like a cone. But with PAW, that arc is forced through a tiny little hole in a copper nozzle. This focuses all of that electrical energy into a tight, straight column, almost like a laser beam. This concentration jacks up the energy density, and that's what lets you weld faster and deeper than ever before.
Now, I keep throwing this word plasma around, so what is it? Well, in this case, plasma is just a gas, usually argon, that's been heated up to an insane temperature. It gets so hot that the gas itself becomes ionized, which is just a fancy way of saying it can suddenly conduct electricity. So it goes from being just a gas to being the super hot tool that does all the work. And when I say insane temperature, I'm not kidding. The plasma jet can reach around 30,000 degrees Fahrenheit. To put that in perspective for you, that is literally hotter than the surface of the sun. Now you can see where all that power is coming from. Now, to make all this happen, you actually need a two-part gas system. First, you have the orifice gas. That's the argon that flows through that tiny hole and becomes the plasma. But then you have a second gas, a shielding gas, that flows out of a bigger outer nozzle. Its job is to form a protective bubble around the weld, keeping the air out so you get a clean, strong joint. So here's a puzzle. How do you even start this thing? You can't just tap the electrode on the metal like with some other welders, because it's tucked away inside the nozzle. The solution is really clever. It uses what's called a pilot arc. A small, low-power spark is created inside the torch, between the electrode and the nozzle. That little spark is just enough to ionize the gas, creating an electrical bridge. And only then can the main, high-power welding arc travel across that bridge and leap to the workpiece. And this diagram here makes it all crystal clear. See that? There are two completely separate circuits. You've got the power source for the pilot arc, which just creates that little spark inside the torch to get things started. Once that path is created, the main power source for the transferred arc kicks in, sending all that welding current down the plasma stream to the metal. And you know what? That whole pilot arc setup unlocks another level of control. It actually lets us run this whole process in two completely different modes, depending on what we need to do. Take a look at these two setups. The only difference is where the electricity goes. On the left, in transferred arc mode, you can see the workpiece itself is part of the circuit. But look to the right, in non-transferred mode, the entire electrical circuit stays inside the torch itself. It seems like a small change, but it has a huge effect on what you can do with it. So let's break that down. Transferred arc is your powerhouse mode. The workpiece is in the circuit, which means you're dumping the maximum amount of heat and energy right into the metal. This is what you use for most welding jobs. Non-transferred arc, on the other hand, is the finesse mode. The workpiece isn't part of the circuit, so the energy transfer is much lower, which is perfect for really delicate jobs, like welding paper-thin materials.
All right, now we get to what is honestly the coolest part of this whole process: It's called the keyhole technique, and this is where you really see the raw, focused power that we've been talking about. It is absolutely wild. The plasma jet is so forceful, it doesn't just melt the top of the metal, it literally blasts a hole clean through it, the keyhole. But here's the magic part. As the torch moves forward, the molten metal from the front edge flows perfectly around that plasma stream and solidifies behind it, sealing it up and leaving a perfect, deep weld in its wake. And the advantages of this are just huge. I mean, think about it. You can get a perfect weld all the way through a piece of metal half an inch thick in just one go. That saves an incredible amount of time. And because you're heating it so evenly from top to bottom, the metal doesn't warp or distort nearly as much. That means less time grinding, less time fixing parts, which saves a ton of money. So with all this power and precision, where do you actually use something like this? Well, as you can probably guess, you use it in places where you absolutely positively cannot afford to make a mistake. We're talking about the aerospace industry for building the parts that keep planes in the sky, or the medical field, making surgical tools and even implants that go inside the human body. Precision is everything there. It's also critical in automotive and even nuclear fabrication, basically any field that demands the absolute highest quality. And look at how versatile it is. It works on all these critical metals, from carbon and stainless steels to aluminum and titanium. And the range of thicknesses it can handle, it's just incredible. From 1/1000th of an inch, which is thinner than a human hair, all the way up to an inch thick. Now, before we finish, we have to talk about safety, because this is a big one. All that intense heat creates extreme levels of ultraviolet or UV light. But here's the really dangerous part you might not expect. Even the low-power pilot arc, when the machine is just sitting there idling, is pumping out enough invisible UV light to give you a serious sunburn or damage your eyes. So full protection is absolutely non-negotiable. So there you have it. When you get right down to it, it all comes back to that simple squeeze. A simple idea that turns a standard arc into a superpowered precision tool capable of incredible things. It really makes you wonder, doesn't it? With this kind of precise power at our fingertips, what new materials, what new structures will we be able to build next?